Then let's go ahead and get started. Where we left off on Tuesday is we were focusing on Tuesday primarily about host discovery techniques. Just another way to phrase the concept that if I have an IP address or a range or a list of IP addresses, can I determine if there's something on the other end of the wire there, right? That if there's some sort of host or machine available for which I can further target. We generally want to go more than a little bit deeper than that. So now, given an IP or a list of IP addresses for which we know there's something there is some host on the other side of that address, we want to figure out, can we determine what type of services are running on that machine, and potentially what versions of those services, as well as things like what operating systems are available here. This is definitely a little bit more, art than science. There isn't one guaranteed way to necessarily determine that this particular piece of software is running on this particular piece of machine. We want to go back to that sort of detective, investigator, inspector analogy from Tuesday and realize that there's techniques we can attempt, things we can try, and we can determine what we can learn. One of the sort of conventional approaches and sort of old school approaches is referred to as banner grabbing. And this is taking advantage of something of a software feature where for several well-known services and applications and software, as part of their application, as part of the application level protocol, they return via text some information either before or during the actual communication at the application level. That's referred to as the banner. Just this piece of text that gets returned in addition to, before, during, it's returning the actual information of interest, and grabbing that banner is just an attempt to say, I'm going to attempt to connect to this machine and attempt this particular service. If I get something back, that actually does tell me something more than what I previously knew. Now, there's probably a sort of an arbitrary combination or infinite combination of potential services and ports and things we could check for, but in practice, there's really just a handful of them that would have any likelihood of returning a valid banner. So when we talk about banner grabbing, it works for a few types of services that we can attempt to connect to. So this is the example we left off on Tuesday, and I wanted you to give it a go and at least look at it and have a feel for what we think might be happening here. So we talked a little bit about our sort of bash shell scripting and how we tend to kind of chain different little shell applications together, provide some input, connect it to an application, take the output of that application, use as the input for the next application. That's a very common sort of design pattern in all sorts of shell scripting. And this is just another example of that, where we're starting with a printf command, which I think for your programming background, we have a general feel for what that is doing, and it's no more, no less than that in this context. Display a particular string of text. In this case, the text is get, in all caps, / http/1.1 plus a line break, as well as host, and the value for host is just an arbitrary value here. The host is just the character Z here. Take that value, take that text string, pipe it to the next command, in which case this one is netcat. We've played around with the cat command, which gives us the contents of a file. Netcat can be thought of as taking the context of a file and sending it over a network connection. And that's exactly what it's doing. Network cat of a file. In this case, we're connecting to a website which we have reason to believe would be accessible via HTTP. So we're going to netcat to that particular website and connect to it via port 80. And we get our results back out. And I can just run that pretty quickly here to show you what I'm talking about. One second. Okay. So printf, get, HTTP, netcat, and I'm going to then take that result and pipe it to less. And what are we starting to see here? Just looking at some of the text that's being returned, there's really two things. What are the two things that's being returned by that command from that server? I'm open to suggestions. Sure. Actual web page, right? Yes, actual HTML. And there was a time where everyone would be really fully fluent on HTML, raw HTML syntax, and it's maybe less of a necessary survival skill these days. But you can see HTML tags here to start the web page, to have a header, to have a title. We can actually scroll down a little bit more. and see the actual contents with a paragraph and a line header. And we can open up the website HTTP Forever and see what it is. It's meant to be just to show that you can still run HTTP websites, although it's really not the standard default these days. And the other thing that gets returned is what we were exactly talking about, the actual header information as well. Information that's returned by the actual web server, the application that is hosting this web page and providing this web page, telling you a little bit more about that service itself. In this case, it's returning an HTTP status code of 200, which is okay. I made a GET request. I got an okay straight back. And we can look at like the syntax for that. And we're really just following kind of the expected syntax for how we do GET requests. Every time you open up a web browser and go to a web page, and if it's making an HTTP 1.1 request, you are essentially, via your web browser, sending these strings out and getting these kind of results back. In our case, it looked a little different than the example here because we're just getting the top level. So we just did get slash, which is HTTP 1.1. The host is not strictly optional, but if we know exactly which domain we're interested in, because we actually provided the name of the domain here, we don't have to specify a host. Hence the syntax was host, just some arbitrary data here. And then we're getting this information back. We get both the actual web page we're interested in, as well as that banner information back. Now that we have this new, relatively less fuzzy projector so that you can actually see while we're here in class what results we're getting back, what can you tell me about this web server? And I think it's okay is if you look at this and you don't instantly know exactly what this is, that's okay. After today, you'll know exactly what this is, and that's fine. But for those who do know it, what web server is being run on httpforever.com? It's called Nginx. And that's just one example of many web servers. This is the server itself telling us exactly what it's running on Ubuntu. And what version of Nginx? I think it's reasonable to assume it's version 1.18. Is that interesting to us as the ethical hacker? And why? And we want to make sure we don't actually take down this particular web server here, which is not controlled by us. But I think that would absolutely be the next thing. My curiosity at least would lead me to believe, okay, Nginx version 1.18, is that last month's version? Is that last year's version? Is that last decade's version? And for web servers, when there's an update, it's usually for a very good reason. I went to the download page of Nginx, and we see that we are currently on version 1.27, for which the stable version is 1.26, and going all the way back to 1.18, that's potentially quite a while back. We can look at the change log for 1.20, which that's also still fuzzy, and compare to, we were at the previous version to that. That's November 2021. So this is a web server that is, I think it's fair to say, most likely running a fairly old version of the software that uses to host a website. It's not actually a guarantee based on how various packages get put together for various operating system distributions. And we will talk about this a little bit later in the semester. Just because it reports back that it's version 1.18 does not necessarily literally mean it's the 1.18 that you download from that website with all flaws or vulnerabilities that were available in that version. Fixes, and certainly for security fixes, can get backported, but it's a good starting point. We can look at that and say, hey, this might be an old version of that web server. Not necessarily our job here today to look at this and try to determine what kind of vulnerabilities there may be, but I just looked in my eyes, glanced towards the word security. 1 byte memory overwrite, which doesn't sound too bad. That's just 1 byte. What all can happen? Well, once you have 1 byte overwrite, you have a foothold in the system. Might occur during DNS server response processing if the resolver directive was used, allowing an attacker who is able to forge UDP packets from the DNS server to cause worker process crash or potentially arbitrary code execution. And it gives a CVE number associated with that. We will be learning a little bit more about the CVE process, as well as some of like the alphabet soup that's kind of associated with our CVEs. But in fact, for that version of Nginx running on that sort of arbitrarily selected HTTP compatible website, We do have a CVE, we have a potential vulnerability, and not only that, we have sort of a severe one that's well known, one for which if we're willing to look a little deeper, we can look online and find all sorts of exploits, proof of concepts provided for that. We are not going to do that today, but it's very possible that as we're just doing that banner grabbing kind of step here, connect, see if there's a web server running, get a header back or an SSH server. Just by that little bit of information, we have a lead, at least. We know where we can potentially go next. So when we talk about both that sort of footprinting and reconnaissance step, as well as now this new scanning and enumeration step, we are doing that detective kind of work based on a reasonable set of well-known ports that we want to explore further. Can we then determine what kind of services are running on that machine, more about the information about the particular host, so that we can then go to the next step. Okay, given this server, running this service, running this version on this operating system, is there something next? We'll get to that eventually. For now, it's all about the different techniques we can use to determine what kind of services are running. So I mentioned banner grabbing, and banner grabbing works for a few different services that still kind of display text banners as part of the attempt to connect to them. That's not sort of the standard way of doing port and service discovery. This other technique, referred to more broadly as port scanning, is considered still really the state of the art of determining what services are running. So port scanning, as a formal definition, is the process of connecting to ports, usually TCP ports, but it can be UDP ports as well, for the purpose of finding what services and applications are running on the target device. What we did on the prior slide is not exactly port scanning. We were explicitly just trying to connect at the application level to a particular port. That will work for a few. If you know that it's running a web server, you can do banner grabbing. If you don't know what's running on the machine, and if it's not a web server or a few other servers for which you can do banner grabbing, you usually have to then turn to port scanning. And when we talk about Nmap, that was really the intention behind the original design of Nmap, was to be an efficient and relatively stealthy port scanner. With the caveat we talked about briefly on Tuesday, that there's always going to be a trade-off between both efficiency, efficacy, speed of the port scanning, and the relative stealthiness of it. It's a very qualitative trade-off. There's not like a numeric value for that trade-off, but the more stealth you attempt to scan, perhaps the less effective your scan, but the less likely the scan itself would be detected. And that in lab, that's not necessarily our concern of trying to avoid firewalls or intrusion detection systems. So we just use effectively default options, and we learn what we learn about the resulting system. That's in your academic kind of controlled, closed box environment for this class. In practice, you may want to consider some of these more stealthy options that Nmap provides for you. And while we tend to think of the ports running on a system as being either just open or closed, open meaning waiting, listening for connection, closed, not waiting, not listening for a connection, Nmap at least differentiates between several different states that a port could be in and has several different types of classification. Really, the first three are the most important, still open, closed, but then also Nmap, via some of these different options, is able to determine if a port is potentially in a filtered state. That we attempted to reach that state, we didn't receive confirmation that the port was open or closed, but based on how we attempted this connection and what happened as a result of that, we have some reason to believe that there is some sort of firewall that's intentionally blocking requests to access that particular port, which is also very important to know as well. If we want to know not just what's open or closed, but what other types of intrusion detection or filtering or firewalling is happening, then Nmap does provide those options for you to explore that. It's a little bit of a dry topic, so I attempted to include various Nmap-related memes on each of these slides, but I didn't really put effort into making sure that they're actually funny. So I can attempt to explain these, but it doesn't really make them funny at the end of the day. So in this first one, attempting kind of a default Nmap connection like we tried on Tuesday, gets a result back, the host seems down, it's blocking ping requests, it's blocking ICMP, so pass -pn to port map. He then tries to Nmap with -pn to skip the ping itself, gets a result back that no, the host is still not down or still not up as far as I can tell, and then he gets frustrated and basically just tries everything in one fell swoop there. So that's nmap dash VVV for very verbose output, dash A for, I think it stands for aggressive or for all, basically try all the service and OS and other fingerprinting, provide a reason why a given scan didn't work, attempt every single script in the scripting engine, we'll talk about that later today, and then try all ports from port 1 through 64K for that IP address. So it went from default port to a non-ping port to try every single possible feature that nmap does and report back those results. So if you have to explain the meme, it's not funny. Not as straightforward, this port scanning, as connecting to a port, though that is going to be a valid approach to take, which is, I want to determine if a port is open, literally just attempt to connect to the port. If you succeed, the port was open. If you fail, the port might be closed. That is a starting point, and it's really the first example we have here. But then in terms of that trade-off between both speed and effectiveness as well as stealth, that turns out to be, while maybe it's kind of a, I wouldn't say default, but sort of an obvious approach one could take to determine if a port was available or not, it's sort of very bad in that trade-off in terms of both speed as well as effectiveness, stealthiness of the attempt to do a port scan there. It's a bit monotonous. We'll get through it relatively quickly here today. But to start with, we have to understand and go back to and review our TCP headers and flags. On Tuesday, I briefly brought up our IP headers and flags to show like what a ping can look like, and I think we covered that sufficiently well for our purposes. For now, I think it's sufficient, although we've talked about it a little bit already, to recognize that as part of our TCP connection process, there are various flags we optionally turn on or off as part of that process. There's the synchronized flag, there's the acknowledge flag, the final data flag, reset flag, and then there's both a push and an urgent flag here. And we already brought up a version of this slide previously, but it's important in this context, is our sort of default, built-in, expected way of making a TCP connection, which is to first have a packet that is setting the synchronized flag. We then wait for a packet that has both the synchronize and the act flag set, at which time we complete the three-way handshake and we actually send an update to the packet with the synchronized flag saying, I requested, yes, I'm here, okay, thank you. That's our three-way handshake here. And when you see documentation referring to something as a full connection scan, that is what it is attempting to do. It may not feel like it's an attempt to port scan because it is just literally connecting to the port, but in some systems you may not have permissions to do anything more than that. To do a TCP connection scan, generally your system would have to allow you to attempt that because otherwise you wouldn't be able to connect to any network devices or services at all. And you don't need to have supervisory or administrative access to be able to open that up. You can use whatever built-in operating system API you have to open up a socket and make that connection. And that's all that's happening here. So if you pass -ST, you're doing a TCP connection or a full connection scan. And if that port is open and listening, you will get that result back that it's open. But if you have any sort of intrusion detection system, any sort of logging system, it's sort of built in by default to kind of check and log that actually happened. So we talked about trade-off of both performance. It's going to be slower. You're really just calling, user level socket code. Stealthy, it's not going to be stealthy at all. It is a very standard connection, so it's going to look like any other piece of software attempting to connect to that particular service. And whether it's effective or not, really, it's kind of a limited kind of piece of information you're getting back out here. That's not the default scan in nmap, but I think you can think of it as like the sort of the baseline for what's the very least we can do to do a port scan. What is the default scan? It's referred to as, S is for either stealth or for the synchronize scan here. It's referred to as the half connection scan. This diagram doesn't actually do a sufficiently good job of explaining what's happening here. But as the name somewhat implies, you're not going through the full connection. You're going through half of the connection here, not the entire connection. So you're still sending that first packet with the first flag. You are then waiting to see what happens. And depending on whether or not that port is open, closed, or filtered, you're going to get 3 results back. And I don't think we have to become TCP experts to know for certain that this was the case, but according to the spec, If the port was open, you're going to get a SYN ACK back, like in the previous attempt. If the port is closed, you're going to get a reset flag set back in the returning packet. And if the port is being filtered, you're going to get nothing back. And oftentimes, it's hard to differentiate whether you're getting nothing back just because of a slow connection. So Nmap in this default kind of mode will probably try a few of those packets and a few of those to see whether or not it's truly filtered or whether it's just a slow connection here. The reason it's called a half connection is because then we terminate the request instantly. That's what I'm not really showing here. So if we do get any of this back, if we get a reset back, we don't have to do anything. If we do get this, yes, I'm here back, we just shut it down. We send a reset flag back and say, sorry, didn't mean, wrong number, didn't mean to actually access your resource. Please don't log me. Now, that is sort of the default connection that Nmap uses. Nmap has been around for a very long time. So whether it is stealthy or not is kind of a relative term. It is stealthier than making a full connection, but it's really not stealthy in the sense of it is the default and has been the default for a relatively long time here. So any intrusion detection system worth its salt should also be able to log that type of attempt. There are those other flags as well, and it turns out through, you could call it a quirk or just sort of a contractual verbiage in the TCP RFC that says that depending on what flags one sets, and in fact, even if a packet is sent with none of those flags set, that a correctly compatible, legally, obligated response should be, there should be, if the port itself is closed, there should be a reset request provided in response. Now, in practice, not all systems are equally compliant. These things are written, and then someone at an organization has to then implement software to actually adhere to that spec in one way, shape, or form. But because of that sort of contractual loophole, whatever you want to call it in the RFC for TCP, you have now these other flags, or optionally, the null scan is not setting any of those flags. And if the resulting system on the other side is actually adhering to the spec, I send a TCP packet with none of the flags set, not even a request to connect flag at all. I should get a reset flag packet back if that port is in fact being closed. So while that doesn't necessarily tell you whether a port is going to be open or not, it can tell you certainly if a port is being currently filtered or if it's actually just not available in that system. And it may seem a little bit of a subtle point. It's very useful to know whether or not something is closed or whether it's being filtered out, right? That tells you gaining more of a footprint into the overall firewall perspective of the resulting system or network or organization. So knowing what things are filtered is a very valuable piece of information. And just because a port is closed now doesn't mean it's always going to be closed. So being aware of what ports are potentially listening is also a very valuable piece of information to provide. So when we talk about these three different variants of the sort of loophole scans here, there's null, meaning none of the flags are set. There's also the fin for the finish with the connection flag being set. And then there's so-called Xmas scan in which the fin, push, and urgent flags are set. Why do we have all three of these types? It gives you a little bit more of a subtle way of interrogating the firewall and understanding what may else be happening. It also can give, and if you look at the Nmap documentation, it talks a little bit more about this in actual detail. It also then may wind up giving you a little bit more about OS fingerprinting itself. Because we have something in RFC, it has to be translated from sort of almost legalese, technical spec to implementation. We have different software teams at different organizations implementing that specification in different ways. In this case, it turns out that if it's a Windows system, it always returns reset, but then you can tell that it's a Windows system based on some other field that winds up getting set in the resulting packet. It turns out that in practice, that while a specification may say that everything should be responding a very particular way, different implementations have subtly different responses that wind up happening. And that's how we can, even via just sending a network packet, a TCP packet, start to determine that, yes, there is something on the other side of that packet, even if it's just returning with a reset response. And actually, I can determine if it's Windows or not via just sending that particular type of packet. And that's a pretty useful piece of information to get back out. Any thoughts why it's called the Xmas scan when you have all three of those flags turned on? Sure. That's what it says in the documentation. I really don't know what that means. Three of them are lit up. I guess in certain, configurations for that's the correct answer, by the way. Certain configurations for Wireshark and other network monitoring, there may be little color codes or like almost LED patterns associated with those flags, but three of the flags are lit up. That's why it's called an Xmas scan, and now you'll never forget it. There's other scans as well. The ACK scan is a little different in it's really intended to map out firewall rule sets as well. So this is the ACK scan that only sends the ACK flag, and then if it gets a reset, we know the port is unfiltered, otherwise it's filtered. The TCP window scan is essentially the same as the ACK scan, but it also looks at the TCP window field of any returned reset packet, which allows you to determine whether potentially a port is closed or not. Again, in the lab, we will be primarily doing just the default options for Nmap, but it's important to be aware that that trade-off space between, I guess you could say, the effectiveness of the scan and the subtlety or the ability to be detected that that scan is actually occurring here. There's one more that I think is sufficiently interesting to cover, which is referred to as the idle or zombie scan here. The idea being is that there's now a third machine as part of this arrangement here. I'll try to walk through it in a way that's relatively straightforward. You can look at this diagram, but I think that takes a little bit while to digest. The idea is that there's an additional field, incrementing IP identifier, that gets incremented in various ways across all the IP packets that are sent in a given system. And so we can actually take advantage of this as well as a third, relatively idle system to determine whether a port is being responded to or not without really implicating your own IP address at all. So there's a third machine involved here. If you want to look at the one over here, I mean, they're the same diagram with just a slightly different result. Let me try to walk through what the idea is here. That you have your own machine, like we have attacker or someone doing the pen test here, and you have the victim or the host, the machine that you're looking to try to do some port scanning on, and then you have an additional idle host here. And the idea is that it's supposed to be idle. It's not supposed to be otherwise, partaking in a large amount of network traffic. So you actually, via that IPDID flag, you actually are that field. You're actually first sending that probe to the idle host, and as part of that, you're getting a response back. And for purposes of just illustration, assume you get a value of 1, 2, 3, 4, 5. That is an incrementing request that we are making here. What you can then do is you can then spoof a packet as coming from that IP address. Now, using your own kind of user level socket code, you can't do that. But if you have the access, if you have sufficient privileges to craft your own raw sockets, it's just another field in the IP header, right? There's no requirement that that actually corresponds to your own IP address. So that second step is what's a little bit different here. We have this additional machine, and as part of the input to the command, there's a separate IP address that you're specifying. Stage 2 is you'd be requesting a scan of that particular port, and you're manipulating the packet as if to pretend to make it look like it's coming from that other machine. And you can then determine, based on what has happened, without ever actually getting a response from the machine itself. So you spoofed a packet is coming from this. The response then is going to go back to the source IP address, which would be that idle host, that third machine that we're taking advantage of here. And while we don't necessarily have direct access to that secondary machine, it's not our machine here, as part of that interaction, all of those values themselves are also going to be incremented, that IP ID value. So we are spoofing a packet from our attacker machine, pretending it's coming from the idle machine. We are sending it. If, in fact, that port is actually going to be closed, it's going to receive some sort of packet back, that reset type information back saying, hey, this port is actually closed. We then try to probe that idle machine again. We probe it in the first place. We get that number like 1, 2, 3, 4, 5. We then spoof the packet. We determine via that spoofed packet whether or not the port we were requesting is actually in an open or closed state. If it turns out to have been in a closed state, then assuming that idle machine is truly idle and is not doing all sorts of other network communication, that IPDIV value for our next probe that happens afterwards should only have been incremented by 1, because no actual network traffic has happened yet on that machine. It just got a reset packet. Whereas if it turns out that port was actually open, and we went from this initial value of request of 1, 2, 3, 4, 5 to the spoofed request in which there's actually going to be a SYN-ACK response we're getting here, requiring that this machine actually send a reset to close the connection because it didn't actually request a connection to that port. That would require that this machine's, the idle host IPDI number, would actually then be incremented 1 additional time. So the actual scan, even though this machine never itself truly requested it, through the mechanisms by which that attempt to connect to that port actually partially succeeds, requires this machine to send 1 additional packet. Then as our attacker machine attempts to probe 1 additional time, you should then get a different result back for that IPID result. In this case, the idle host never has to send a packet other than a request from the attacker. In this case, because we kind of forced it to pretend it was connecting to this machine, it's actually sending 1 additional packet here, assuming it's truly idle and is not otherwise sending all sorts of other packets and incrementing its number accordingly. As we do that initial probe, we wait a little bit, we do that secondary probe, we can determine whether or not that port was in fact open or not. Without this machine, if you see the whole point of this here, having any real reason to believe that this attacker machine even exists, that it's even available, that it's even the one that's doing the scanning. So in terms of stealthiness of it, of course, there's potential issues with true reliability of these type of results. There may be something logged in the intrusion detection system on this victim machine saying someone's trying to connect to this particular port on my machine, but we would have no reason to believe that it was the attacker IP that was actually doing it. It would have no knowledge of any packets having come from that attacker machine. Questions about the idle/zombie probe? Okay. There are other approaches. So that was all TCP based. There are all sorts of relevant, interesting services that are running on UDP instead of TCP. The real challenge, or the sort of the trade-off involved with doing scanning on UDP is by nature of the protocol, and this is something you would have also learned in 230, there is no sort of handshake mechanism, right? So that does kind of change the very nature of how one would do port scanning here. There is no handshake that we're actually looking for to see if it actually succeeds or not. It's a so-called fire and forget protocol in which we send data and we hope for the best, and we hope that we get a response back when we actually need a response back. That makes the actual scanning process a lot more time intensive, because once you send something out over UDP and you get nothing back, you haven't actually necessarily learned anything, right? You may have not gotten something back for all sorts of reasons. So those type of approaches in practice, and you can try it with the -SU flag and Nmap, usually is slow because it's going to require a lot of attempts. To have some reason to believe, well, I tried a lot of different things and got nothing back. Perhaps this potential UDP port is in fact closed. But just getting nothing back doesn't really guarantee it. So it's more of a probabilistic statistical likelihood that a port is going to be closed. Of course, then if you do get some data back, it's kind of akin to our banner grabbing approach here. You got some data, you got some response back from that port, well, then you have some reason to believe that that port is open in UDP mode. In terms of the countermeasures for port scanning, that's the whole real purpose, at least originally, of intrusion detection systems, that they can be configured in all sorts of ways to determine port sweeps and port scanning activity. The trade-off oftentimes is there, just like we talked about the trade-off between the speed of doing a scan and the amount of warning that that scan may be providing. The issue you may have on the IDS side is if you have it set extremely sensitive to really alert you when it's receiving any sort of port scanning activity, you may get too many alerts. And so you need to then almost have a secondary system that is an alert processing, an IDS real-time alert processing system that gives you a more realistic report of, here's 2 million alerts that you received today. Of those, only the following subset are actually meaningful. So it kind of almost pushes the problem to a second stage of software to determine that. But that is still considered state of the art, and there's all sorts of companies who really exist, not just to provide basic IDS, but to provide you real-time analytics of IDS results for your organization. And then in terms of mitigation, I think sort of standard system configuration sort of makes sense, which is, block by default. If I don't have a reason to have this port open, I should not really be listening to traffic on those particular ports. Then when you have a system, you have to determine what is actually being enabled by default, turning things off that you don't actually need. There are a couple approaches that are really more sort of security by obscurity, but could still have some value. If all these tools are assuming that SSH is running on port 22, there's really nothing requiring that. That is sort of just the default expected port for that particular service. If your system allows you to run it on a different port, you gain a very small amount of security by moving it to a different port. There's also this concept of port knocking, which is really not in common practice, but conceptually is also kind of a security by security approach. Whereas I mentioned you could run SSH on a port different than port 22. Here in this case, looking at our telnet port 23 here, the idea with port knocking is it's almost like a secret knock on a door. That's why it's called that. That if a system attempts to just connect by default to a particular port, your firewall system can be configured to say no, nothing's available, there's no service available on that particular port. And then you can configure it to instead respond to a sequential sequence of port requests, like a secret knock. And then only if that particular sequence is received can it then, determine if it'll determine that port can then be left open to that requesting IP address. That's a very high level visualization I'm showing here, but conceptually that's all it really is. If a request comes in for port 23 to begin with, the answer is no, I'm not available. But if instead 867-5309 and then a request to port 12345, if those three requests come in that order from that same IP address, the firewall can then be configured to say, yes, for that particular IP, I'm going to allow port 23 to be open. That's what port knocking is. It has no real sort of cryptographic backing to it. It is what they call security by obscurity. It's made more secure because under the assumption that no one else can be told that that is how that system is being secured. Could have some value to it. It's really not in common practice today. Then in terms of the maintenance side with regards to countermeasures, we have these tools that one performing ethical hacking is going to be making use of. You should be doing it yourself as well. If these are your own systems and you're setting up your own systems and services, you should be running these tools on a periodic basis, and you should make sure that the report you get back kind of meshes with what your expectation is for those systems. I want to talk a little bit more about, now that was sort of service detection. Really, if we're being frank, that was more just open port detection. But we can learn a lot generally about a system based on what ports are open on that system. If ports 139 and 445 are open, it's very likely to be some version of Windows because of the various applications that Windows has historically run on those particular ports. If port 22 and port 11 or 2049 are open, it's probably a Linux system. That is all just, when I say probably, I'm trying to be accurate here with my phrasing. There's reason to believe that the system is running that underlying operating system because for historic reasons, those are the ports that would be open. That's not to say you can't run port 22. You can certainly run OpenSSH on a Windows system. In terms of where you'd want to place your bets are probably better placed on assuming it's a Linux system if it's running SSH. If it's running NetBIOS, an SMB file sharing, and it has those ports open, it's very likely to be a Windows system. We can actually do a little bit more than that as well because of what I mentioned with regards to those nuances between the various vendors' IP stack implementation. Again, we have a specification that says how one should communicate using TCP/IP. These are very lengthy documents. The implementation has to take that spec and translate it to code. And so it's not to say that one implementation is wrong, although historically there has been instances where that's been truly the case, but they're just having slightly subtly different implementations of the same specification. And tools like Nmap using the -O or that -SV or there's a -A flag can actually use some of that feedback it gets via these TCP/IP connection requests and also give a best guess estimate for what kind of operating system the resulting host is running, with not really any great guarantees. I posted a screenshot here, which Nmap actually can detect. I tried it out. Do we know what this is? What operating system that would be? I feel very old today. No, that's not Windows XP. That's okay. Thanks for trying anyway. Thanks for the answer, I guess. Now I feel even older. That's fine. Which one came first, XP or Vista? I don't even remember. This was a while back, but XP. Okay, so I feel ancient in the back. Sure, older than Windows 95. That's Windows 3.1 or 3.1.1 Windows for work groups, which was really the first Windows operating system that had any networking stack itself. Now, if you actually find a Windows 3.1 system in the wild, you should rub your hands together with glee because presumably there's all sorts of things that it would be vulnerable to. But those are the kind of things that service detection can actually provide for you. The operating system itself isn't broadcasting, although some services do, as we saw, isn't broadcasting what the operating system is using, but just based on how it actually is handling these TCP/IP packets, you can actually make some determinations about what the resulting system is running. We have a little bit more I do want to cover with this, but we're not required to finish it all today. So let's leave things here for right now, and we'll finish this topic up on Tuesday before we jump into the next week's topic as well. Otherwise, good luck on Lab 2, and I'll see everyone on Tuesday.